Okay, well, let me first introduce our panelists. So one of the people who are going to be answering questions in the background is Kumar Ghosh. He's a quantum engineer at E.ON Digital Technology. In his current role, he is working on various applications of quantum computing in the energy sector. Prior to E.ON, he was a postdoctoral researcher at Purdue University in the US and on the faculty at the University of Denver in the US. He holds a PhD in theoretical physics from the Karlsruhe Institute of Technology in Germany. Welcome. We also have three panelists from D-Wave, Victoria, David, and Tanvi, who are work with our sales team and support our customers. Our speaker today, Marina Fernandez Campo Amor, is a quantum computing incubation specialist at E.ON Digital Technology. In this role, she supports the exploration of use cases in the energy sector using quantum computing while providing business value. She holds a double Master's of Science degree in Industrial Engineering and Mechanical Engineering from UPM in Madrid and TUM in Munich, with a focus in energy technology as well. She has an honors degree in management and technology from CDTM. So thank you very much, Marina. And with that, we can get started.
Thank you very much, Susan, for the kind introduction. Also, thank you everyone that is joining this webinar from everywhere in the world. Today, I'm happy to represent E.ON to introduce you to the last work that we have done with D-Wave called Community Detection in Electrical Grids using Quantum Annealing. As Susan introduced to you, we at E.ON are the largest operation in Europe, and we mostly have two business units in the sense that we operate energy networks and we also provide customer solutions. So we operate a variety of networks from energy to like gas and power to also heating networks. And we have also many industrial sites and also connected assets. And we are over 70,000 employees and we operate in about 15 countries all over Europe, which basically puts us in a very ideal position to help drive Europe's energy transition, leading to this fundamental transformation of the energy world. But what exactly do I mean by this transformation in the energy world? For decades, we have been used to relying on carbon intense and centralized energy assets. So country-wise, you'll have a few powerful generation sites that were responsible to satisfy the overall energy demand and could be relatively easily steered by determining the amount of fossil fuel to be burned. But things have changed drastically and very rapidly. The energy sector is facing a threefold revolution. Technological advances have made it possible to cost-effectively exploit renewable energy sources like the sun, water, or the wind, and to increasingly decarbonize the energy production. At the same time, due to the very nature of these resources, power generation is increasingly happening at decentralized manner, and the increasing number of assets at play and will increase the overall complexity of the energy systems. Now, we at E.ON, we have been profiting from the rise of digital and IoT technologies. So this allows to, for example, connect all this decentralized world and act as a fundamental enablers, allowing unprecedented interactions between different players, so customers, producers, utilities, or grid operators. So the grid systems are becoming increasingly complex, interlinked, and they require higher level of coordination. So at E.ON, we are leveraging the power of AI and also quantum to make smart, decentralized, flexible grids a reality. What are some of the examples? So for example, with congestion management, when you have the location of the generation and the demand are different places, there could be some bottlenecks in the grid. So how can we use the data to stabilize it again? Or how can we optimize energy storage? So what is the optimal charging schedule for a fleet of electric vehicles? Or how can we exploit this to improve building energy efficiency and grid stability? So basically, how can we use all the batteries from electric vehicles as a massive battery to stabilize the grid? Also, local energy markets. As said, future energy systems will be more and more decentralized, meaning that we will find more assets at the household level, for example. How can we enable a peer-to-peer energy trading market? So how can we enable that prosumers and consumers will exchange electricity? Or how can we use that a local energy system where we're completely off the grid? So these are a bit the questions that we have been solving using AI. But in quantum, our journey starts in 2019. Actually, we have been working with two main partners, D-Wave and also IBM. And we are a team of full-time quantum engineers, plus we also supervise some master thesis, some PhD students through academic alliances with different universities, but also research institutions. Our focus is to solve real-world use cases which have potential to deliver business value at E.ON. So what are these use cases that we have been exploring? So in terms of technology, we can separate in the two main quantum tech frameworks. On the one hand, we have been using quantum annealing for optimization problems, but we also have been using universal gate-based quantum computers using quantum machine learning or quantum amplitude estimation. This might sound a bit abstract, but in terms of topics, we could cluster it in, for example, flexibility services and the way that we can use small energy assets such as photovoltaic or batteries or these electric vehicles that I was already mentioning as a way to provide flexibility to balance the generation and the demand. Also, we have some work on smart assets and predictive maintenance. So as said, we have many assets and we want to operate them in the best way possible. And last but not least, we have also worked on risk and portfolio management. So in this many assets, we need to assess what are the risks that we are encouraging and what is the best combination of portfolio. And you can actually can find some of this work online in the archive. But today we're going to focus on the latest work using D-Wave, that is the community detection in electrical grids / peer-to-peer, and you will understand why. So to give you a bit of context on where we are in Europe, right now the European Commission has developed a more ambitious goal towards renewable generation and has set the target to achieve 40% of renewable generation by 2030. Now, this will require that we will increase the number of assets, and of course, at the household level, the role will change. Right now, most of us, we are consumers, but whenever are able to produce electricity through, for example, photovoltaic panels, we are no longer consumers, but we are prosumers, consumers that can produce. Now, this gives new opportunities as new energy markets can be envisioned and in fact are gaining strength. But this also comes with challenges. So how are we going to deal with congestion? Our generation demand going to be always balanced? What is the role of the DSO? The DSO, it stands for Distribution System Operators, and are the companies that manage and operate the grids. So how their role will change? Also, how can we accommodate these new market players? No? So this is the question that we have in mind when we started these projects. So at the end, the future of the grid will become more complex, more decentralized, and of course, bidirectional. The flows of electricity will be in the two directions. So how we started this project was actually asking ourselves, if we would have a local energy market, and you will have, imagine on the right, have someone that has photovoltaic panels, so wants to has some excess of energy and wants to sell it. And then on the left, we might have a consumer that wants to engage in this local energy market and wants to buy this energy. But they're a bit far away, right? Would it make more sense if these two could trade instead? So you could incentivize this local, like even more local energy markets. At the end, the closer they would be, the less losses that you would incur. Now, that's the idea behind this work, is to how can we split the grid into meaningful groups? So the research question was, how can we optimally detect these communities in the grid, but take into account technical characteristics of the electrical grid? So the electrical grid is not like any other graph, for example, and you need to take into consideration the material characteristics of the cables, for example, how it operates. What are the benefits that it can bring us, this community detection, this splitting of the grid? First of all, we want to couple the markets, so the economical part of energy exchange and the revenue that you could get with the infrastructure, because it's very crucial. At the end, we always have to maintain generation and demand at the same time, and this is a bit difficult. So therefore, this is a way on how to already cut down the problem. Now, in power grids operations, it's very important to conduct power analysis. Problem is that this power analysis take up a lot of computational resources because the relationships between the equations are quite complex. Therefore, if you would split the grid into meaningful groups, you could also partition this power analysis and simplify it, and therefore use less computational resources. And last but not least, as I mentioned it before, trying to incentivize local energy exchanges will reduce the power losses in these particular transactions. So this is a bit the idea behind, but how did we do it? No, like what are the principles that we use to split it? So we use a concept using complex network theory that is called modularity. So you can read the definition there, and I will present to you a bit the math, but don't be discouraged. In simpler words, modularity is a metric that will find meaningful structures when we partition the grid. So instead of having all the lines at random, the higher the modularity will mean that how we split the grid has a meaningful structure. And for you to understand a bit the math behind, if we have a graph like the one on the left, so we have very simple graph, only 3 nodes, so 3 points, and 2 lines, or edges that connect these points. So we have something called the adjacency matrix. So this is a matrix that represents the graph on the left. So basically on the top row, it gets described how the node number 1 is connected to node number 2 and number 3. And you can do that for every single node. So basically we're using this adjacency matrix. The degree of each bus or node, bus is a bit a jargon for electrical grids. It's usually how you call the nodes in electrical grid. And also edges will be called lines. So the degree of the bus is how many connections a node has. So for example, node 1 has a degree of 2, whereas node number 2 and number 3, they have a degree of 1. And then the M is the total number of edges in the graph. On the right of the equation, you see a delta CVCW. That is a factor that will be 1 if the 2 nodes will be in the same partition and 0 otherwise. So we will go element by element and sum it all up and get the modularity matrix. And in this case, our goal will be to separate the grid into 2. So are these 2 in the same partition? Yes or no, 1 or 0. Having this concept in mind, what we wanted is to not only have this metric, but include the information of the electrical grid. As I said, is very important. In this case, what we use is to give a weight to each of these elements of the adjacency matrix. So they will not only be 1, but they will have a value. And this value is calculated given a composite weight, meaning that we will include 2 weights at the same time for 2 different metrics. One is the light resistance, and the second one is the sensitivity of the line. So line resistance basically means that if you have the cable, so the big electric lines, how easy or hard is that the power flows, so the electricity flows through this line. So at the end, the more the resistance, the more losses that we are going to have. And the second one, the sensitivity of the line, relates to the fact that if you have one cable and you have a transfer of energy, so a difference of energy, so suddenly someone decides to generate a bit more and pour it into the grid, how the line is going to react in terms of power flow. So is it going to not notice it because the flows are going to be redirected, or is this line going to take up all the power flow? Taking up all the power flow can cause that will reach a dangerous limit. So at the end, you have a limit of power flow for each line, and you never want to reach it. Therefore, we wanted to combine how the power flow goes easily through the lines, and also how they react to changes to find these meaningful partitions or communities inside the grid. So coming back to the main question, therefore, the question comes to the fact of how can we partition an electrical grid by maximizing the electrical modularity, no? So take into account all these composite weights and all this information that we can extract from the different grids. So having this concept in mind, how we do it, or what is the workflow for this project, it kind of encompasses 4 steps. So first of all is the data preparation. No? So we have a grid, we have to characterize it, we get the data from the grid, and that we of course need to calculate this coefficients, which is not trivial calculation, and then with those coefficients in mind, so we have the grid characterized as a graph with these weights. Then we need to prepare the problem for the specified backend. So what do I mean by that? At the end, we want to optimize the partition. So we are going to maximize this modularity, but depending on the tool that we want to use, do we want to use quantum? Do we want to use classical? We need to prepare the problem in a different way. So once we have this problem prepared in our code, then we sample the problem, we solve the problem. Of course, we have to solve it multiple times, and then we post-process the results. So in terms of the data that we use, we have been using 3 test cases from the IEEE, that's the Institute for Electric and Electrical Engineering, so it's the biggest world association for electrical engineering. And they have several data sets to test out different algorithms or methods within the grids, no? And we wanted to use different sizes of grids to be able to understand how these quantum methods would scale. So for you to understand a bit the categories of the elements, as said, buses are the nodes, the different points that we saw on the graph is usually how we call it. Then the lines are the electrical lines that connect these nodes. And then these buses and lines are what we are going to actually use for our algorithm. Additionally, in these data sets, we can find information on different loads. So, for example, we could envision as devices that consume energy, generators that are devices that will produce energy and pour it into the grid. And then we have other 2 categories that just a bit as a curiosity. We have the external grid, so the connection to external grid, and then the trafos or transformers, which basically is a device that changes the voltage from high voltage to medium voltage to low voltage. No? So we can switch the voltage of the line. So in this case, you see that we're going to start with a very small graph, meaning that it's only 14 buses. They will go to a bigger graph with 33 buses and 118. And there we'll use more hybrid methods. But I will explain it later on what I mean by that. So once we understand the data, we extract the weights, we have characterized our grids. Now we need to describe the problem as a mathematical problem, as an optimization problem. So we start with the idea of modularity, right? So we want to maximize this metric. But if you're familiar with D-Wave, usually you want to run a problem that is binary. No, we want to use binary variables. And at any optimization problem, you usually have three main elements. You have your objective function, your goal, your objective, what you want to maximize or minimize. Then you have your variables, your decision points, and then you have the constraints. So we don't have a free lunch. We have certain constraints in our problem, no? So that limits us. Now, starting with the binary variables, I introduced this modularity metric and how it was stated would partition the grid into two parts, not like 1 and 2. Now, if you have a big grid, you wouldn't expect to partition the grid into only two parts, not two communities. So you want to expand it to more communities. Therefore, now the decision point that we want to solve is, does bus I or node I, a particular node, belong to which particular partition? So the group or partition K, no? So our binary variable is going to be 1 if bus I belongs to group K, and 0 otherwise. So at the end, what we have is a collection of binary variables for all the nodes and all the partitions. So if you remember matrices multiplication, if you would multiply a vector of all the nodes, so xi, x1, k, x2, k, until all the nodes, times a matrix and again the vector, that's how you reach a scalar, so a number, which in this case will be the modularity. So we're going to populate this matrix with the values of the modularity. And here we already went through all the possible combinations. The end is almost like a matrix. And then what we want is to not just have it for two partitions, but to multiple. So we are going to sum up all these matrix multiplications for as many partitions as we want. So we will have K partitions, and therefore we will have K vectors, but we will use the same matrix. Now, as said, every optimization problem or most optimization problems have constraints. So what we don't want is that a node will belong to 2 or 3 or more partitions. Therefore, we need to limit. So here we say that for every single node in the bus, the sum of all the variables in all the possible partitions will be 1. So one node will be in one group and no more. Now, this was done as a binary integer programming problem. So it's a binary problem with constraints. But in D-Wave, the way to be able to solve it using the quantum annealer, this problem needs to be transformed into something called a CUBO problem. So a quadratic and constrained binary optimization problem. Here, the way that will be done is this problem will be embedded into the quantum hardware, and we will reach, we will let it run and basically reach a point of minimum energy. So at the end, we want to minimize the function that you see on the right. But we need our ways to transform it, the one on the left to the one on the right. So for example, to transform the maximization into minimization, there's a very simple trick into which we switch the sign, for example. And for the constraint, what we did is transform this equality into a quadratic formula. And then we need to sum it over all the buses, as we here have a constraint per bus. So at the end, the problem on the right represents the problem on the left. Also, something that it needs to be added is for the constraints in CUBO problems, we usually weight them. So the name of quadratic unconstrained means that there's no hard constraints. Therefore, we need a way to kind of enforce these constraints that we want to enforce. No, so we give a particular weight to kind of counteract the objective function. And in the literature, it's not clear how to pick this, so there's not a proper formula, but it's usually done through experiments. That's how we actually did it. Now, once we have defined our CUBO problem, we want to run it and we want to solve it. So in terms of tools, we use 3 tools from D-Wave and 2 classical tools. So the first one, the D-Wave sampler, actually is able to embed the problem into the quantum hardware and run it on real hardware through the cloud platform that D-Wave provides. Also, the Leap Hybrid sampler and the Leap Hybrid DQM sampler, that's a bit the same, but what it actually does is split the problem, and some parts are run in the quantum hardware and some other parts are run classically. Because we're able to split the problem, that means that we can take up bigger problems. And therefore, that's what we use for the IEEE 33 and also the IEEE 118. Now, of course, in this type of research, we need to benchmark it. We use 2 classical methods. One is Louvain algorithm, and it's a heuristic that gives a bit of rule of thumb. What is the optimum number of partitions for the optimum modularity is pretty common in this context of complex network theory and also modularity optimization. And then we use Kurobi, that is a state-of-the-art it's linear programming and integer programming solver. And we picked this particular one because it was one of the few that would allow us to run quadratic programming problems. At the end, the objective function is quadratic, and then we haven't found that many open source solvers that could take up this type of problems. It usually requires some sort of transformation. So now that I introduced the backends that we use, what are the results? So what results have we achieved in this paper? So on the left, you can see a table with the results for the modularity for the smaller grid, so the 14 node one, for different number of communities. So something that we achieved was to find actually slight better results, even in this small example with the D-Wave sampler. Why is it so? We know that quantum is probabilistic, and we run it multiple times. So within this sample set that we reached, that we got after solving it, we were able to find a slightly better result. No, as some of the other methods that are heuristic will stop probably at a minimum, at a local minimum and not at the global minima. So this gives a bit of the hint that this method would actually give us better quality of results. Now, in terms of time, of course, we need to compare it in terms of solution and also in terms of time. So in this case, Groby is faster than the other methods, and that's because the problem is still relatively small. And for the quantum methods, there's a bit of a caveat here. So if we start from top to bottom, the hybrid ones, we are reaching the minimum time. So we cannot go below 5 or 3 seconds in each, because it's kind of like the minimum time that has to run for each of the hybrids samplers. In the D-Wave sampler, the thing is that to run it only once, to run one anneal is like around 20 nanoseconds. And of course, it scales with the number of samplers. So here we're sampling 10,000 times. So of course, it's going to take around, so as you see, 2 seconds. If we were able to run it in less time, therefore the running time will actually decrease. But there's always a trade-off between the number of samples and so the running time and the quality of solution, because the more you sample, the more probable is that you find a very, very good solution. So why are we using this hybrid thing at all? No, so I explained that it's because of the size, but what does it mean? So here actually you see a example of another tool from D-Wave, that is the D-Wave Inspector. So this allows you to visualize not only your problem, but also how it is embedded into the quantum computer. So on the left, you see the graphical representation of our problem, of our optimization problem. So each node in the graph represents a variable, and then the edges represent the different relationships between the variables. So it has nothing to do with the representation of the grid. So it's a bit different. Now, this graph problem has to be embedded into the QPU, so the quantum processor unit. Now, because the qubits are not fully connected, therefore, sometimes you need to do kind of a trick where one variable will not represent on one qubit, but multiple qubits. So you will have a chain of qubits that represent a binary variable. Of course, if you have multiple qubits that have to behave as one, and you have a big chain, that creates more probable that this chain might break, and therefore your solution is no longer representative or the problem that you're trying to solve. Also, another thing with chains is that you need to enforce this property that all act as one variable, and therefore you need to give something called a chain strength. So it's kind of a hyperparameter of the problem. So usually in this case, we use the one that D-Wave calculates on its own, but it's something that we can tune to get better performance, but it also can affect the performance of the problem. So it's something that it has to be analyzed separately. So if you go bigger and bigger with your problem size, then it becomes increasingly harder to find a suitable embedding to your problem. And therefore, hybrid methods are a pretty good solution to bridge this gap, no? So now if we go to the next grade, so the one that is the IEEE 33 bus test case, here you see the different modularity results for each partition. So here you can see how the number of binary variables increase with the number, of course, it's linear dependent between the number of nodes and the number of partitions. So it's basically the multiplication of the two. So embedding a problem of 300 variables, this particular one at least, was quite hard. Like it's very hard to find an embedding, and therefore we use the hybrid. So something that we observe is that for this particular problem, the Leap hybrid DQM sampler, and DQM actually, I forgot to say, but it stands for discrete quadratic model. It gives us the constraint kind of for free. So it's very optimized to give this constraint of only this variable can take up this value. So how it's coded or envisioned is that each node will be a variable, and then each node can take up, so imagine we want 9 partitions, then it can take up to 9 partitions. And it's done in a way that it's very optimized to try to find the maximum objective function fulfilling this constraint. So that's why we believe that we obtain better results with the sampler than with the hybrid sampler. To get better results for the Leap hybrid sampler, probably we will need to twitch some of the parameters of the CUBO problem. So this is in terms of quality of the solution. If we take a look again at the time performance, we observe that the problem is still relatively small for the hybrid samplers, and we don't surpass the minimum time for any of them. So we're still kind of 5 and also 3 seconds of running time for all the hybrid samplers. But in Gurobi, we start to see something different, no? Like whenever we increase the number of binary variables, then the running time starts to slightly increase. And in fact, when we go to a bigger graph, the 118, although we see that both DQM sampler and Gurobi obtains a very similar solution, Gurobi is not able to converge. So after 1 hour, we had to cut it off, whereas LEAP hybrid DQM sampler achieves the solution in around 6 seconds. Whenever we try to kind of compare, okay, if we only let it run for about 6 seconds, both of the methods, the quality of the solution in Gurobi was a bit, so it was worse. So here it gives another argument to see that these methods could be a good candidate, no, for quantum annealing. And what you see on the right, of course, is how the partition would look like, no. So in first eye, you can see that the partitions that the method is able to find, they make sense, no, even if you only look at it visually, no, without taking into account the modularity matrix. So in terms of conclusions for this work, we have seen that, or we can theorize that quadratic objective functions create a very good candidate for quantum annealing. So there are not a lot of solvers that can take up these quadratic objective functions, and therefore we thought that this problem was very suitable for this particular technology. Also, we have also seen that these hybrid samplers can bridge the gap between the current state of the quantum hardware and scalable applications. At the end, this particular problem will not make so much sense if we run it on a small grid. No, we want to scale it to a big grid. Also, modularity optimization can be applied to electrical grids, and actually a nice tool because you can also change the weights that you want to give to your lines. Now, so you could play around with other metrics that would characterize the cables of the electrical grid. And also, we wanted to make use of the time to thank D-Wave for the support, and particularly Victoria Gulliver. She has helped us a great deal to push the project forward, also explaining many of the concepts that we use for this particular project. It has been invaluable in the past months. So now, okay, this is the conclusion. Seems like it's over, but what's next? No, what
Okay, well, we have some questions. Thank you so
Yes,
much,
sorry.
Marina. Great talk. We had quite a few questions answered during
Okay.
your talk, but we saved some for you.
Okay.
One question is this just a digital twin, or is D-Wave being used in real-time operations?
No, this will be a digital twin. It's not in real time operations.
Okay. Isn't likelihood high that all community members want to sell when there's sun or buy when there's no sun at a given point in time?
I mean, it's not realistic at the short term because not everyone would have a solar panel. So that's one thing, that you will have some users that will have solar panels and other ones that they will not have. And also, I would expect that if you would run this, you will not be individually trading, like you will have some sort of algorithm that will trade for you. So you would kind of forecast when is the best time for you to trade. So that everyone will trade at the same time in the same direction, it doesn't seem plausible.
Okay. Are any of these elements can be understood as a self loop in a regular graph?
That's a very good question. I don't have the answer, unfortunately, for that.
Okay. Will this model be adapted to be dynamic?
That's actually one of the things that we are working on right now, to find what are the weights that we could give to make it a dynamic algorithm, and also to run it in, like, for example, with a cloud architecture and run it continuously as a continuous optimization.
Okay. How do the results you showed for the quantum methods with D-Wave compare with a Lovain method?
With the what, sorry?
Lovain, L-O-V-A-I-N.
I'm not aware of that method, but I'm happy to know more about it. So you can contact me afterwards.
Okay. Let's see. So many of these have already been answered. I think someone's typing an answer, but we'll make this the last question. Is it possible to use classic software and hybrid method with quantum computers for optimization?
Yes, it is possible. Actually, it is possible with some of the D-Wave open source libraries to create your own hybrid algorithm, something that we are also investigating at the moment.
Okay. What was the probability of obtaining an optimal solution, i.e. how many runs were needed to obtain such a solution? And how does it scale with graph size or other parameters?
So for each of the runs, we run it 10 times, and then we run 10 times with 10,000 samples for each method, especially for the quantum annealing, so the D-Wave sampler. We will need to run it on a bigger scale to understand how what would be the O notation, for example.
Okay. And last one, will these models become part of machine learning tools?
Yeah, I could see that happening.
Okay, all right. One last one came in, and well, they just continue to come in here. Let's see. Have you encountered any problem where introducing a constraint just only improves the solution time?
Can you repeat the question?
Have you encountered any problem when introducing a constraint where introducing a constraint only improves the solution time?
Not that I'm aware of. At the end, the model was pretty simple. So objective function and constraint. We didn't try other constraints. It's something that we also are looking into, what other constraints could include and how the problem would scale.
Okay, well, wonderful. I think we've come to the end of our time. Just a note, as I mentioned at the beginning, that this talk will be recorded. It will be posted to the D-Wave YouTube channel in the next few days. Anyone interested in the slides, if you just send an email to sales@dwavesys.com, DWAVESYS.com, we will get them from Marina and be happy to send them out, thanks to E.ON. So Marina, Kumar, thank you so much for doing this. We really appreciate it. Hope you enjoyed it. And thank you everybody for attending today.
Thank you very much, Susan. And thank you everyone for attending as well. Ciao, ciao.